Sí. Para presentarles al profesor Daniel Berliner, que es profesor de la Escuela de Gobierno de la London School of Economics y que amablemente se ofreció a dar esta clase abierta sobre este tipo de análisis, y nada más diría que esto ha sido aplicado en un análisis muy amplio de solicitudes de información. Y fue un análisis de contenido de how many? Freedom of Information Request. 1 million. Entonces, tiene potencial el método. But I know, but no, it's the same methodology, ¿no? Y bueno, y nada más. Daniel, all yours.
Thank you so much. Okay, I must speak into the microphone. Thank you so much for having me. I'm always happy to be here. I'm Dan Berliner. I'm at the London School of Economics. So this is an introduction to computational methods for public policy, machine learning, and text analysis. There's going to be 2 parts to this. Part 1 about machine learning, part 2 about quantitative text analysis. You will see these are very closely linked together. I want to emphasize this is non-technical, this is conceptual, okay? So I'm not actually going to be able to tell you in this brief period of time how to do these things. What I'm going to do is talk about what's the menu of tools that are available and what you might use them for, okay? And how you'll know if they're useful. I'm assuming no prior familiarity except with general quantitative methods like regression, and sort of, thinking in terms of what a data set looks like. So yes, applied. We're going to talk about different tools, how they work conceptually. There's no math on the slides. And honestly, the assumption here is, how will you know what would be useful for whatever goals you have so that you can decide, am I going to invest the time in learning this tool, or am I going to seek out a collaborator or hire a computer science undergraduate? That type of thing. And what I'll tell you is, for me in my own research, some of these tools I will carry out myself, but for many of them, I work with collaborators who are more technically skilled than myself. But what you need to know is how to bridge the method to the application. So this is what we'll be doing. And so I'll hope that you ask questions if something's confusing or if you think it might be useful to elaborate on something as we go. And then if there's time, there's a portion at the end when I'll ask you what might you use some of these things for, if we have time. Okay, what is machine learning? The goal of machine learning is classification, placing observations into classes or categories. This is closely related to prediction. If you can classify the future ahead of time, you can maybe predict it. Machine learning is divided into 2 main types, what's called supervised learning and unsupervised learning. Right now, we'll talk primarily about supervised learning. If you're doing supervised learning, you are using existing data to train an algorithm or a model in order to classify things. You train a model to take what you know already and classify things, and then you apply those patterns to things you don't know in order to classify them. Thank you. And we'll go through quite a few examples about that. Whereas unsupervised learning is automatic. So supervised learning requires something where you've already coded what you want to know. Here, I'll just give an example. A good running example will be tweets from Twitter. So let's say we have we've downloaded millions of tweets, and let's say we want to know something very basic. Which ones are angry? Now, what we would do with supervised learning is, let's say we had 1 million tweets, and let's say we code by hand 1,000 of them. And we code them yes or no, 0, 1. 1, it's angry, 0, it's not angry. But say we use these 1,000 that we've coded, and we develop a model to predict based on what else we know about the tweet. What words are in the tweet? What emojis are in the tweet? And we predict in the 1,000 that we hand-coded, are they angry or not? We predict if they're angry or not. Then we take those patterns and apply them to all the others, where we don't know if they're angry or not, and we predict based on the words that are in those tweets. Are they angry or are they not angry? So supervised learning requires that first step. You have to already know what you're interested in for some subset of them. Maybe that's because you code them yourself, or maybe that's because you have some shortcut in the world. There's some ground truth that exists already. Unsupervised learning doesn't use that first step. You don't tell it initially what it's looking for. Unsupervised learning looks for clusters, latent patterns that sort of emerge bottom up from the data. Now that lets you skip this first step, but what it means is you get these patterns that might not mean anything, and it's up to you to interpret those patterns. So we'll go through this in much more detail, but that's the main difference between these two types. Supervised learning, you're developing a model to classify or predict something specific that is already known in some subset of the data. Unsupervised learning doesn't have that step. It looks for patterns that emerge bottom up. Okay, I'm going to talk about two examples of ways in which we might use supervised learning. The first would be where our goal is measurement. The second would be where our goal is prediction. And this will hopefully give you an idea of the sorts of empirical settings where these can be useful. So this is very much like our tweets example. Measurement might be where we have 100,000 documents of some kind, and we want to measure something about them, but it's too many to code them all by hand, right? If we had 1,000 documents, we could code whatever we wanted to know about them. If we have 100,000, that's not feasible. And this might be the case of blog posts. Which ones are about politics? News articles, which ones are about corruption? Tweets, which ones are angry? In some of the work I've been doing, responses to information requests, which ones are non-compliant? So what you might do to employ supervised learning as a tool of measurement, right? This isn't really something that produces theoretical conclusions, right? This isn't a regression model that gives you coefficients that maybe tell you something about the world. This is using this as a tool of measurement to give you a measure that you then use in some other way, right? Then you get a measure that you can use to examine empirical patterns or as a variable in a regression model. So this is just a measurement tool. We do what we said. We take a few thousand of them, maybe a few hundred, it depends, and we code them by hand, or we have a team of researchers to code them by hand. Maybe we need to pay close attention to intercoder reliability in that setting. Sometimes we have a ground truth already. Maybe sometimes you're looking at contracts, and some of these contracts have already been declared unfulfilled or non-compliant in some matter by some administrative process. And maybe you could use that as your ground truth. Greg.
Ground truth is keywords? Is that what you mean?
A classification that is already verified. So,
Yeah, but if I'm looking through the tweets,
yes.
I'm going to be looking for, so essentially, training the machine to look for certain keywords?
Yes.
Right?
But it needs to first, the model needs to first know what to look for. So if I want to code which tweets are angry, how does a computer model know what angry is? I have to first tell it, here's 1,000 tweets in which these 500 are angry and these 500 are not angry. That's the ground truth. The key principle here is you can't get something from nothing. You can't just magically have a measure of which tweets are angry without first having a measure of which tweets are angry in some smaller setting.
Is this technical jargon, ground truth?
It's an attempt to be non-technical jargon. Like, what's the truth on the ground?
Okay, but it's not. You wouldn't put this in a published article, ground truth.
It's used in that setting sometimes. And so what we would do is develop a model to predict among 1,000 posts. We first verified these 500 are political, these 500 are not political. Then we develop a model that uses the attributes of them, like the independent variables, to predict which ones are political, which ones are not political. So the model learns what features, such as words in the document. A document means observation in this setting. Words in the document or variables about the document that best predict this outcome variable within the training set that you hand-coded. So again, just go back to tweets. We've created a training set, the set of data that you use to train the model. Let's say 1,000 tweets, and we read each tweet, and for that row in the data set, we said 0, it's not angry, 1, it is angry. And now we have a data set where every variable is a word. Does the word appear in that tweet or does the word not appear in that tweet? So what words might be informative for whether a tweet is angry or not? Swear words. Swear words might be informative for whether a tweet is angry or not. What's a non-swear word that might be indicative of whether a tweet is angry or not? Maybe. No comment. The angry face emoji. So basically, we have these 1,000 tweets, the training set. And we now train a model that knows when I go look at a new tweet, if I see angry emoji, if I see swear word, if I see Trump, I'm going to call this one an angry tweet. And if I don't see these things, or if I see the happy face emoji, or if I see happy words, I'm going to call this not an angry tweet. But the first step is to train it in the set of data where you know the outcome variable, 0, 1, is it angry or not? And then you can predict that for the others.
I understand your example with Twitter.
Yeah.
Because it's a short character thing, but in blog entries or articles, it's a larger document.
Yeah.
And if you look for Trump, I don't know, it could appear many times, and this don't mean that it refers to political or, yeah, I think that it's more difficult because the large
So
end of the document.
let's just hold this for a moment, because the second part of this about text analysis will deal with this issue in more detail. So we'll absolutely come back to that. This doesn't just have to be words. This could be numbers. So this could be predicting. Let's actually go to the next page, because this will be some more numeric rather than non-text examples. Is it okay? So example 2 might be prediction. Maybe we have a real-world outcome that has been observed in the past, but we want to predict it or forecast it in the future, perhaps to enable a policy response. So here's some examples where this has been used. Where and when does conflict or violence take place? Who will default on a loan? Which public contractors will fail to deliver? Which information requests will be denied? These are the exact tools that are used in the private sector. Which movies will people like? If you have Netflix and it recommends you movies, this is the precise set of tools that are used. They're using machine learning models to predict which movies you will like or not like based on features of the movie and features of you that Netflix knows. Or in much of the private sector, online advertisements. E-commerce companies have massive data science divisions to predict which ads people will click on or not click on. So these are where these tools might be used. So something like who will default on a loan? What features, the equivalent of independent variables, might be predictive of who will default on a loan? Income? Credit history. So these are numbers, right? These are numeric variables that are used to predict these things. And now this sounds bad, but the financial industry does this. They use these tools they have predictive models for who will default on a loan or not. So these predictors can be numeric as well. And so in this case, what is the training data? Who has defaulted on a loan in the past? So you have past people. Think of a spreadsheet, and every column is a person or row. Every row is a person or a business, and every column is a feature or a variable about them. And then you have a final column, yes or no, did they default or not? Now you have future people about which you know everything except that last column. You know all the other variables, but you want to predict Yes or no, will they default on a loan? Similarly, people use this for conflict forecasting. The United States Defense Department is spending a lot of money trying to develop models to forecast or predict conflict. And they use their data on where in the world there's been conflict in the past, and they have all the variables about each country or each location, and they're using where there has been conflict in the past not to develop an explanatory model. This isn't about regression. They don't care about the causal relationships. All they care about is what is predictive. And they want to know which are the features that predicted conflict in the past, and then maybe those can predict that empty column, whether or not there will be conflict in the future. Now, this effort has performed very poorly on the whole, but the United States Defense Department pours massive amounts of money into it. And so exactly that. Develop a model that best predicts the outcome in the past based on observed variables. Use those same variables for subsequent instances of the same process to predict the outcome. I'll give you one example. We've only just barely started doing this, but say for information requests. In principle, you could develop a system that knows in the past which requests for information are denied or not, or get a positive outcome or not. And then before I submit a new information request, maybe I type it into this system and it gives me an estimated probability of success. In practice, that probably wouldn't work very well because this is such a noisy process, right? This approach will work best for predictable processes. This approach will work the worst for unpredictable processes. So I hope that those examples gave an idea for what you might use this for, right? In the first setting, we're using this for measurement, right? This is simply a tool to get a measure that we then want to use for something else in a setting where it's too costly or time-consuming to code everything by hand. In the second setting, we might be substantively interested in prediction as its own goal. In a public policy setting, maybe we want to predict things in order to provide a policy response to them. The biggest challenge here is this necessity of having the ground truth. Having the thing that you're interested in, the outcome variable, already known for some subset of cases. You can't get something from nothing, right? This is not magic. It also requires the predictors, the features, the independent variables. You need to have those as well, right? If we're trying to predict conflict, we need to have collected data about the areas or entities or jurisdictions where we want to predict conflict. If we are trying to measure or predict something about text, we'll get to this in a few more slides. We can use words or attributes of the text as the features. Okay, now, how is it actually done? It's very complex and it's very technical, and there's many different ways to do it. There's dozens and dozens or even hundreds of varieties of technical ways to do this, right? I described this process. Then you have the choice of which hammer do you use to carry out this process. At a very basic form, logistic regression is a form of this. So actually, some very simple machine learning models just use logistic regression. There are other types of things. If you've heard of random forests, or if you've heard of support vector machines, or if you've heard of neural networks, these are all just technical tools to accomplish those series of tasks that we just discussed. So what I would do is just collaborate with a computer scientist at that point. But you need to know what you want to do and why. Now, the benefit here is that these approaches, especially some of these more complicated ones, they can include more complex combinations of covariates. Think of a regression model where you don't just have, think of a regression model where you have 20 independent variables, but you also include every possible interaction term between every possible combination of those 20 independent variables. If you were actually running a regression, that would be insane, and you should never, ever do it. But in a machine learning model, that's often done. Because again, the goal is not explanation or understanding. The goal is simply prediction or classification. So again, right, how is this different from ordinary regression modeling? Right, because we're talking about there's a dependent variable, an outcome that you want to know, and there are independent variables. And in some cases, logistic regression, the same technical tool would be used for both. But what's generally different is sort of the conceptual approach. Usually, if you're doing this type of supervised learning, you don't care about explanation or causation. You just care about prediction. The Defense Department does not care if there is a true causal relationship between variable 13 and conflict. They only care if this variable can predict conflict. Maybe it's not causal at all, but if it has predictive value, they're interested in it. And on the other hand, sometimes when we're doing regression work, sometimes a variable will be statistically significant, but has a very tiny effect. So you could have variables that have a true causal impact, but they're so tiny that they are of useless predictive value. So it's a different conceptual approach to what you want to do. You wouldn't do this if you're interested in explanation or causation. It's about prediction and classification. Okay. What are the dangers? The biggest danger that requires a whole extra series of steps is the danger of overfitting. You might develop an algorithm of this kind that can perfectly predict the past, but is useless to predict the future. Maybe it can perfectly predict the data that you trained the model on, but it can't predict anything outside of that. So this is the difference between in-sample and out-of-sample. So the best practice here, remember I said you take that training set of data, let's say 1,000 tweets that we hand-coded. Are they angry or not? We actually need to divide it up into two parts, a training set and a test set. So we train a model on half of that data, and then we test it on the other half. So in these 500 tweets, which words or emoji predict angry or not? But then we're going to test how well that actually worked in this other half of data that we held out, that we kept aside. And we want to do that before we unleash this model on the unseen data. So there's an important series of steps to evaluate the performance of this kind of model before you actually apply it. So when you see terms like training set and test set, that's what this is doing. The test set is data where you still need this ground truth. You still need to have values in that column of your outcome variable, but you're using them to evaluate your model before you deploy it on the unseen data. Second concern, there are trade-offs between false positive rates and false negative rates. Let's just imagine, this is just for emphasis, no one should ever do this. Let's imagine that the police developed a model to predict who will Let's say the police developed a model to predict who will commit a crime. This is ill-advised, but let's say they did it, okay? And they've done this type of model, and they use features, attributes of people to predict, are they going to commit a crime or are they not going to commit a crime? There's a trade-off between more false positives and more false negatives. More false positives means you are falsely accusing more innocent people of committing a crime in the future, right? You falsely assign them a positive value of their classification or prediction. False negatives is the opposite. You've missed people who maybe will commit a crime. You've given them a 0 when they should have had a 1. And there's no solution to that. If you maximize one, you lose out on the other. If you minimize one, you lose out on the other. It's always a trade-off. And if one is ever deploying these rules in a policy setting, this will have real human consequences, and you have to decide which worry is more dangerous.
Like Minority Report, the movie?
Exactly. Hopefully it never happens.
Exactly.
Okay, were there questions about supervised learning except for the issue of text, which we'll come to shortly? What might you try to use this for, practically? either for measurement purposes or for public policy purposes.
If someone is going to participate in a corruption act, for example,
Okay.
or maybe if someone is going to bribe to some officer.
Okay, or maybe if someone is going to accept a bribe, who will accept a bribe? I'm not saying that's a good idea, but perhaps it could be applied.
Maybe evaluation of public policy based on previously implemented similar policy.
Okay, so even at the policy level, success or failure based on the past. Now here's something where I should have said, another warning. Sorry? This is only useful if you have more data than you can deal with by hand, right? So for something like policies, maybe we have a data set of 600 policies and if they succeeded or failed. 600 is probably few enough that whatever you want to know, you should just study the policies encoded by hand. It's when you get to the point where you have maybe 3,000 up to millions or billions of observations that you would want to use these tools. If you have a feasible number of something, probably just do it by hand.
It's the same like big data analysis.
Exactly. This is used for much of big data analysis. It uses precisely these tools. Exactly. Okay, unsupervised learning. I'm only going to say a bit here because this will come out much more clearly in the text analysis section. Whereas supervised learning, this just repeats the previous slide, uses existing data to train a machine learning algorithm. Unsupervised learning, you don't have an outcome already defined that you're interested in. You simply automatically classify data into clusters, into patterns. But then after the fact, you have to decide what they mean. This will make sense. Oh yeah, here we go. Unsupervised learning, it finds latent clusters or structure in data. It does not require training data. So if you've done a factor analysis or principal components analysis, that's a pretty simple version of unsupervised learning. If you've ever worked with networks or seen people take a network and find clusters in the network, that's a kind of unsupervised learning. So you find clusters, but what do the clusters mean? It's up to you to interpret what the clusters mean, because you haven't given it already this outcome to learn about. It needs human interpretation to understand the results. There's no direct way to evaluate the accuracy without comparing back to something that's already been measured. This again brings you back to ground truth. So for example, maybe we want to cluster countries or provinces based on policy patterns. Maybe we have a massive data set of 40 different policies for every municipality in Mexico. We could find clusters. What would those clusters mean? You would have to examine the results to decide what the clusters meant. As we'll see shortly, you can cluster texts or speeches into topics, what they're about. You can find clusters of nodes in a network. Okay. On to quantitative text analysis now, which will employ more of unsupervised learning. Before we get to that, any other non-text related supervised learning questions? Okay. Now you know what machine learning is. Now you know what's the difference between supervised learning and unsupervised learning. Now you maybe can know if they're useful for your own purposes or not. Text analysis is more fun. Quantitative text analysis. Our goals might be any of measurement, categorization, classification. The approaches are going to include both supervised or unsupervised approaches, as well as simpler approaches like dictionary methods, which we'll explain. What's the assumption that you make? The assumption we're going to make if we're doing quantitative text analysis, the assumption is we can represent text as data. Usually, not always, usually, this relies on an assumption that we call bag of words, the bag of words assumption. Take a sentence of speech and disassemble all the words from each other. Throw all the words into a bag and shake up the bag. You have removed any information about word order. All you know is which words were there. The bag of words assumption means that you ignore word order and you represent each document as a vector of zeros and ones. I'm going to show you this here. We have 3 documents. Each document is a sentence in this case. What is your name? My name is Dan. Dan is over here. We can represent these with this. This is called a document term matrix, and this is the basic ingredient of almost all quantitative text approaches. We represent these 3 documents as a series of zeros and ones. Every column is a word. Every word that possibly appears in this corpus. The corpus is what you call your data set of text documents. Corpus just means data set of text documents. That's it. So the word is gets a 1 because it appears in all 3. The word Dan, 0, 1, 1. The word name, 1, 1, 0, and so on, and so on, and so on. That's the bag of words assumption. That's representing text as a document term matrix. Now, suppose our observations are legislative speeches or news articles. This is going to be very, very big because let's say we have a data set of 350,000 news articles. How many total words are going to be used across all of those? Millions and millions and millions. So you often make another assumption, a sort of sparse term reduction. You maybe set a floor. Like, I'm going to dump out all words that don't appear more than 10 times or something like that. Or I'm going to require that a word appear in at least 1% of my documents to include it. And then you usually reduce your data set to manageable size. So, maybe 3,000 columns instead of millions and millions of columns. And the columns are just this, zeros and ones. For every document, which words appear, which words don't appear. Now that's a severe assumption because, like you said, think about, for very long documents, think how much is going on, and think about human speech and human language. A lot of the information comes from word order. You can think of examples where the order of words matters a lot for their meaning, or where what one word means depends a lot on what word comes after it. In practice, the bag of words assumption performs shockingly well. When I've done this sort of work, I'm shocked at how well it works, despite throwing away word order. If you want to retain word order, there's a few different ways you can do it. If you have specific terms that are jointly meaningful, let's say conflict of interest. Maybe we want to treat conflict of interest as one term. We don't want to break apart conflict over here and interest over there. If you know what those are, you can manually fix them, right? Search every conflict of interest and just replace the space with an underscore. So now you're treating it as a single word. There's much more complex methods that dispense with this assumption altogether, but they're very computationally demanding. Other common steps, stop word removal. A stop word is the, and, things like that. We remove those because they're not informative. Word stems. Often you reduce words to their stem, right? So let's say corruption, corrupt, corrupted. Maybe I want to treat those as the same thing, and so I run my text through a dictionary, a stemming dictionary, that reduces all of those to corrupt. And these stemming dictionaries exist for almost all languages in the world. They exist in Spanish, they exist in Serbian, they exist in Arabic, they exist in Mandarin. You just have to find them. Okay. And so again, these are all things we would do if we have too many documents to code by hand. Even if you have 1,000 documents, just read them. It will take a while, but... Okay, so we gave this example of a document term matrix. Now, what will we do with this? I'll talk about a few different things we can do. Simple is dictionary approaches. Sentiment analysis is the most straightforward version of these. There exist lots of dictionaries of word sentiment, right? So we can think, let's say we just think of sentiment as one-dimensional. Negative, neutral, positive. Negative sentiment, anger, sadness, rage, disappointment. Positive sentiment, happiness, being pleased, etc. And so there's dictionaries, right? There's dictionary. You can download a spreadsheet with thousands of words, and for each word it has -1, 0, 1, right? Negative word, neutral word, positive word. And then you run your document term matrix through that, right? For every document, every word that's there, we multiply it by that sentiment indicator. And then for every document, we get a total sentiment score. So this has been done for movie reviews, right? You run movie reviews through this, and if movie review 1 has 100 positive words and 5 negative words, its sentiment score is 95, et cetera, et cetera. Somebody has done this for economic news. They ran millions of economic news articles through this sort of sentiment dictionary, and they found that the sentiment of economic news coverage tracks time series of economic performance and time series of public economic confidence, things like that. I've developed like dictionaries of words about corruption, scandal, fraud, irregularity, and sort of you can run things through that to get an initial measurement of which things are about corruption. You can also develop your own dictionary, right? If there's something very specific. Oh, a friend of mine studies gender and politics, and she was studying the Ugandan parliament, and she developed a dictionary of gender policy-related words because she wanted to know, do female legislators talk more about gender-related policy than male legislators? And so she used a dictionary method where she had a set of words, relatively straightforward. Supervised learning. Let's see if I have this on another. Okay. Supervised learning we talked about already. Think about tweets. So this is exactly what we spoke about before. We want to know if tweets are angry or not angry, or if they are about politics or not about politics. Or I once saw a presentation where computer scientists wanted to classify if tweets were sarcastic or not sarcastic. This turns out to be an extraordinarily difficult problem, and they could barely do it. Not very well. So this would simply be, we want to measure something about text. Now, so what you said, let's say news articles are very, very long. It depends on practice if it works or not, right? So for a news article, you would have your document term matrix, and there would be a number for how many times each word appeared, or for whether or not each word appeared. And it depends if for whatever you wanted to know, is the pattern of words informative enough at categorizing those articles by what you want to know or what you don't want to know. And it depends. If I want to know something sort of easy to separate, is this political news or is this celebrity news? We could probably do that. But if I want to know something much more complex and contextual, then it might not work. And as always, with all of these, whatever your output is, you have to examine it, and you have to spend a lot of time assessing, has this worked or has this not worked? Because what you don't want to do is just run a model, get your results, assume that it worked, and not actually know that your results were junk, because the thing you were trying to classify was not too contextually deep to classify. Unsupervised learning. This is where unsupervised learning is most useful, I think, for text. And this is where the tools that I've used the most. And I'll show you a bit about on the next slide. Topic models. Topic models are models for categorizing texts into topics. Categorizing texts into topics. What I'll actually do is talk about that right now. What a topic model does is cluster documents into topics, like categories, based on sets of words that tend to appear together or not appear together. If a cluster of words usually goes together, this type of model calls that a topic. This can be applied to things like speeches, press releases, news articles, social media, government reports, etc. So we've used this There's a paper, Berliner, that's me, Bagozzi and Palmer Rubin, just published in the journal World Development, where we applied this to information requests. If you go to the website of Infomex, you can download all 1 million information requests ever filed with the federal government, federal only. And this includes the full text of the request. So we had 1 million or so documents, and we had the text of the request for each. And we used this. We used the bag of words assumption. Ignore word order. Shake up all the words in a bag. Treat them as a document term matrix. Run them through a stemming dictionary. And just to give an example of some of the clusters of words that came out here, we've unstemmed these to make them more legible, right? So, you know, the O would be cut off for proyecto, etc. But this is indicative of what the results of a topic model might be. These are clusters of words that tend to appear together, and the results call this a topic. But because this is unsupervised, we then have to look at these results and decide what they mean. What might this topic be? Environment. Exactly. These are requests about environment. What might this be? These are the very, very simple, short ones. How do I do this procedure? How do I find a small business loan? How do I do this? Where can I find this? Very, very, very simple. What might this be? What might this be? Procurement. Procurement. So when I first saw these results, I was shocked that it worked this well. There are some settings where it does not work this well, right? Sometimes you run a topic model, you get the results, and it's junk. It doesn't make any sense. You know, you see these words, and there's no idea what they have in common. Also, we didn't just see the words, right? For every topic, we read, I think, 100 requests for every topic to validate our interpretations, to make sure that this was procurement and not something else. So you can't get away without the work of reading things. You had a question? Okay. So hopefully that gives you an idea of what a topic model is, right? Clusters of words define a topic. Well, that's actually what makes this unsupervised learning. These categories were not defined ahead of time, right? We did not start out with a list of categories. We didn't start out saying, okay, we're going to code every request. Is it environment? Is it security? Is it contract? Those clusters of words just popped up. You know, it ran for a few days before the results came out. The results emerge from the data, and they have to be interpreted, and those interpretations have to be supported and defended. There's no guarantee that the results will make sense substantively. Sometimes these perform very poorly. What does the researcher have to choose? Remember, we didn't choose what topics to look for, but the choice you do have to make is how many. The model won't work. You just have to tell it. You tell the model, are you estimating 5 topics, 20 topics, 200 topics? And so that's a choice that often has to be analyzed and validated. So for instance, we ran a few different varieties. Our ultimate paper uses a 20 topic model, but we compared a 10 topic model, 15, 20, 25, 50, 100. There's quantitative metrics that you use to compare them, but most important is qualitative, right? Qualitatively, what made the most sense to substantively interpret what was going on. In this case, when we ran a 10 topic model, procurement and environment were lumped together. So it was more informative with enough topics that they would separate out. But this is going to be different for every application. Question? Okay. We're getting into the weeds now, but there's 2 different types of... The first type differentiation of topic models is mixed membership or single membership. If you ever see LDA, LDA is the most common kind of topic model. It stands for latent Dirichlet allocation, which is a super mathematical term. No one cares what it means. Well, the computer scientists do. LDA, which is what we used, is a mixed membership model. Every document is represented as a mixture of topics. So this is especially useful, let's say, speeches. Not every speech is about just one thing, Part of the speech is about one thing, part of the speech is about something else, part of the speech is something else. So the results you get from a mixed membership model represents each document as a mixture of topics. 50% topic 1, 20% topic 2, et cetera, summing to 100%. You can also use single membership models, where each document is coerced to be a member of only a single topic. This is more straightforward, but it's often useful to have that extra level of information from a mixed membership, because sometimes you can do cooler things with that data later on. There's more complicated things as well. Recently, political scientists have started using something called a structural topic model. This is getting published a lot late. There was a paper 2 years ago, I think, introducing this model, a team of people from Harvard, and now more people are using it. A structural topic model is simply a topic model, but with covariates. So you estimate the topics, like we've just described, but then you say these topics are the dependent variable, and I want to know which covariates explain where there's more or less of a topic. So you could say, okay, I'll just give you an example from a paper of mine. If any of you do any research in the human rights field or are familiar with human rights field, most human rights data across countries has been coded from human rights reports published by the US State Department since 1997. The US State Department every year publishes a report about every country and describes their human rights. And so we wanted to try out this tool, and so we topic modeled those reports. But we also included covariates. So there was, you can't really see this, but there was 15 topics. Killings and disappearances, labor rights, terrorism and torture, elections and parties, human trafficking, prison conditions, et cetera, right? So every report is represented as 20% of that topic, 15% of that topic, et cetera. But then we included covariates. Is the country an ally of the US or not? How much aid does the country receive from the US? How much does the country trade from the US? We also included covariates about the US in that time. Was the president Republican? Did the president's party control Congress? So we could see, for instance, we can get explanatory relationships. US allies reports tended to include far more of the killings and disappearances topic. Countries that the US trades with included far more of the freedom of movement topic. So it's a topic model, but with covariates. In practice, I don't think this was actually very useful. You'd want to be very careful. A lot of people right now, this method is hot these days. And a lot of people are doing it just because they can. I think you want to make absolutely sure that what you would learn from it is useful.
Was that published?
Yeah. Political Science Research and Methods. We were lucky that it got published there. I'm down on that paper. I shouldn't say bad things about my paper. Okay. There's other types of topic models. Supervised LDA. You estimate topics, but you use those topics to predict an outcome. In any case, topics must be interpreted. There's no guarantee that they're meaningful. Because this is unsupervised, you have to do the work to interpret the output and decide what it means. Don't worry, we're almost done. Okay, forget topic modeling now. No, wait, before you forget topic modeling, one more example. This is from one of the earliest topic model papers in 2010, one of the earliest papers to use this. They applied a topic model to Senate speeches in the United States. And so I cut it off. There were 42 topics, but I've just shown you the first 12. Some speeches were about judicial nominations. They included those types of words. Some speeches were about education. They tended to include words like school, teacher, student, children, etc. Are legislative speech transcripts available in this country? So apply topic models to them. That could be fun. Okay. Other entirely different types of text methods than a topic model. Document scaling. Are any of you familiar with ideal point estimation that's used to estimate the ideology of politicians? So sometimes, let's say, I'm sorry, I'll give my example from the United States Congress. People want to measure the ideology of Congresspeople. They want to place them on a scale from left to right. For a long time, that was done using their voting records. You use the pattern of which bills they voted for or against, you do some math to it, and you get every person's placement on a single dimensional scale, left to right. Hopefully left to right. You can do the same thing with this. Instead of every column being a bill, and if you voted yes or no, every column is a word. So people have used legislators' speeches and scaled them. They take the patterns of words that are used to place every legislature on a left to right dimension. Or maybe you combine every speech from one party. You know, say like in Germany, there's lots of different parties. So they combine, for every party, combine every speech together and use the pattern of words to place each party on a left to right scale. There's different varieties of this. Some are more supervised, some are more unsupervised. If you're interested in that, I can send you those papers. There's a danger here. You're placing whatever your documents are on one dimension, but you don't necessarily know what that dimension is. So, long story, but at one point I was trying to do something with Serbian parliamentary speeches. And we applied these to the Serbian parliamentary speeches. The results we got were not left-right, right? Everyone was placed on one dimension, but when we looked at which words and which speeches were indicative of that dimension, the dimension was policy areas. It was how much were they talking about economic policy versus other things. And so this is one issue with an unsupervised approach. You don't necessarily know what the results are going to mean. You have to look closely at it to interpret what they mean. Okay, we did that. Let me just see what's here. Okay, last slide. We talked about dictionary approaches, simple but powerful. We talked about structural topic models. We talked about document scaling. Last thing, you could also think about similarity, right? You can take two documents and measure how similar they are to each other. You could imagine taking every pair of documents among your entire set of documents, and now you have a network of how similar every pair is to each other. What might you want to do this for? Text reuse methods. Have any of you seen plagiarism detectors? You know, you upload your paper, and it runs through this text reuse algorithm that assesses how similar your paper is to this library of other papers. People have used this with pieces of legislation to find instances where, let's say, a lobby group has their model legislation, and their model legislation gets reused over and over and over again in bills. You can measure that sort of similarity. Or let's say you have one reference document that's really, really important. And you want to know how influential. Let's say 10 years ago somebody gave a speech, and that speech is super, super important. Maybe you want to measure how similar all your other documents are to that speech. You can do that. Any questions? What might you use text analysis for, either for research purposes or public policy purposes?
Well, I mean, I wrote a paper that for APSA 2009 that was accepted preliminarily into a journal, but I wasn't able to double code. Not that I would use it for that, but basically the theory is that Mexican newspapers and media tends to be very, at least in the era when I did this text analysis, was very intent on reform. Always talking about reform. If there was a corruption scandal, the newspapers would also be talking about why this happened, perspective, what I call perspective accountability, looking forward, right? There's also retrospective accountability, and that is what Brazil is good at, and where I live, right, where the news is about who did what and why they're wrong and corruption and that they should be destituted, but there's no talk of reform. Probably because the elites in Brazil don't want to reform at all as well. But in any case, I think you'd be able to find text clusters or using a dictionary of terms about reform to identify how prospective or retrospective articles are, especially
Okay.
corruption. So if you took, let's say, a database of articles on corruption, you might be able to process them through this, whatever, using a dictionary approach, and then be able to categorize them as retrospective or prospective and compare different presses across the world treatment of corruption, whether they're looking at corruption as a systemic problem that needs reform or looking at corruption as an individual malady that someone did something wrong and needs to pay for it, which is the case in Brazil, I find, much more than at least Mexico when I was doing my analysis.
So in this case, the documents are newspaper articles.
Yeah.
And the thing you want to measure is retrospective accountability versus prospective accountability.
Right.
And this is a good example because you could use two different tools for this.
Right.
A dictionary approach, which requires you to develop two lists of words, retrospective accountability words, prospective accountability words, where the words can't, if a word appears on both lists, that's not useful.
Right.
Or a supervised learning approach, where you hand code a sample of a few thousand news articles, retrospective, prospective, and then you let a supervised learning algorithm, instead of telling it which words matter, it's going to learn which words matter. The algorithm will try to learn, okay, does the word tomorrow help me predict if this is retrospective or prospective?
Sure.
Something like that. And so you would have to evaluate how well these methods worked.
You might have to actually separate articles into different segments because you're going to get both indicators of retrospective and prospective in the same article.
That's also useful as if you're working with text, you can be creative with what is an observation, with what is a document, right? You could take each speech and call every speech a document, or you could divide every speech up into paragraphs and call each paragraph a document. And one of the variables would be which speech does this paragraph belong to? Or you could, instead of breaking down, you could aggregate up. You could combine every speech from a single political party in a single legislative session as one giant document. So you can choose which level of analysis is most useful to you. Any one more person want to share an idea what you might use this for? Oh, sorry, the microphone.
Is this on?
I am thinking of using text analysis in my work because we usually go to states in Mexico and we create groups to discuss. For example, there are plans that is for the long run. For example, Guanajuato 2040 is a plan for next 30 years. Mm-hmm. And in that tables, we ask to the participants that they, in computer, they write their opinions about what would you like, or what politician or what program do you recommend, for example, in the national strategy or in that way. Mm-hmm. And for example, I think that we could take all that propositions, mm-hmm. and for example, made clustering, and so we could automatically take, for example, that proposals that are about education, maybe health. Mm-hmm. I think that could be useful.
And how many of these comments or responses do you have?
I think that there are like 100, maybe, or maybe more.
Maybe more.
But I think that maybe the problem is that there are short tests.
Short is okay. Tweets are short.
Yes. Okay, there are short proposals, so I don't know if that is good or bad, but...
So I think if you had many, many, many of these, right? If you had too many to read, just read them and code them yourself. Let's say you had thousands. This would be a perfect thing to use text analysis tools with, but you could actually use any of these tools, and you would actually use different tools for different purposes. You could categorize them into topics. You could measure their sentiment, positive or negative. Did they like the proposal? Did they dislike the proposal? You could measure something very specific for a few of them, and then use the supervised learning tool to measure it for all the others. And so it would simply be a pattern of first identifying what you want to know and then selecting which set of tool will get you there.
Yes, I think that even we can use similarity because a lot of proposals are very similar. For example, they say, I don't know, we want a new program to make this, and 3 or 4 people say the same thing. And maybe we can first make a similarity, and after we can cluster.
And so actually, I've met some people who are developing systems to use these, because lots of countries now have participatory policy platforms of some kind, where whatever this platform is, it solicits massive numbers of comments, hundreds and thousands of comments. How do policymakers actually deal with that? The policymakers are supposed to use these as inputs to policymaking, but if there's hundreds of thousands of these, what can they do? So there's people out there trying to use these tools and make them into platforms to give to policymakers to help them make sense of these types of results. Let's see if it works. Okay, thank you, everyone. Thanks for having me. Hopefully this was useful. Oh, yes, one last. Oh, sorry, the microphone.
Do you recommend software like R or?
Yep. Sorry, good question. I should have mentioned. I use R for these. These types of tools have been very well implemented in R. There's an R package called Quanteda, Quanteda, Quant EDA. Actually developed by somebody in the methodology department at LSE that implements a lot of these tools. It's pretty well documented. This stuff has been around long enough now that if you search online, you can actually find lots of lessons. Python is probably better than R if you know Python. I don't know Python. But if you do know Python, that's even better. Stata, you won't really be able to do this in Stata. Yeah, good question. Thank you.
And how much computational power do you need, for example, in your example of 1 million of documents? Is that a lot?
I wouldn't want to do it on my laptop. It depends. Some things are fast. Some things are slow. Some things you can do in a few minutes. Some things the computer runs for 3 weeks and it hasn't worked and I had to give up. Some of the people that I work with will have like Amazon web servers running. So I mean, basically, the more documents you have and the more demanding the method is, the longer it will take and the more computing power you need. But some things are very fast and not very computationally demanding.
Dan, no, I just wanted to thank you. Alejandra had to go out for something, so she asked me to thank you on behalf of her and of the Public Administration Division. And I just wanted to thank you all as well for being here and for your questions. And it was actually very useful. And I took a course last year, as you know, when we met. And I think I learned more during these few minutes from doing this.
It's because that course had too much math.
Yeah. So thank you very much. It was very useful.
I don't do math.
Yeah. Okay.